Yeah, it's streaming online. Ooh, look there. We can see. Hey, Randy. Nice to see you. All right. Okay. So can you see my slides on there? Oh,
Not
I
yet.
gotta share. Oh, that's a good point. I have to share. Will I share my desktop? No. I share. What do I share?
Share screen and you take the double screen. Yes, now let's share.
All right. All right. So should we get going then? Okay, well, yeah, it's recording. It is recording. Is it recording? Let me just double check.
Yep. The Zoom indicator
Let me
says
just
it's
make sure it's recording. Why is it doing this?
the Zoom shows it's recording, Bruce.
This recording, it says recording.
Ah, okay, good. All right. Okay. Well, then we'll just get going then. Okay. Thank you, everyone, for coming to the talk. This is what I'm going to do. I'm going to talk about transformers. I'm going to talk about GPT. I'm going to, it's really 4 parts. I'm going to talk about the amazing thing that transformers are and ChatGPT, really. I'm going to try to explain attention. So it'll be sort of an intuitive look at what attention is. I'm going to talk a little bit about prompting. I'm going to talk about the limits of transformers. Like I'll show some examples of where it fails and talk a little bit about why I think it fails. And then the very last thing I'm going to talk about is some ways that people are looking at to make transformers more intelligent. So just a little bit about me. I'm an entrepreneur, and I have been doing AI in various companies for quite a while now. I'm wearing one of my products is called the Phoenix. It's with a company called Health Gauge. And what we do is we use AI because we take these signals, we use machine learning, and we do blood pressure estimate with signals coming off this device. And we have a entire infrastructure where we take all the wearable signals, they go to the cloud, and doctors can use that information to manage your health. And so we have other versions of AI in the cloud to help you manage your health. Another thing that I'm doing is this product right here. It's a non-invasive blood glucose monitor. I'm actually wearing it. If you see this thing flashing, it's because it's actually taking readings from my skin. And we use machine learning to convert those signals into a blood glucose estimate. We've done a lot of training on it. We know that it works. We're on our way to FDA trials. We've raised quite a bit of money in with MedWatch, which is a company in the US, and they've licensed all of the health gauge technology. So that's and I'm interested in transformers for 2 reasons. One is because we can use transformers to do signal processing, and I'll talk a little bit about that. But the other thing I'm building is something called a health coach, which is a system that uses conversations to go and interact with your health data and help you manage your health situations. So transformers and GPT, transformers are based on attention. If you haven't heard about them, well, then you've probably not been on a computer recently. So they implement what are called these large language models. They're super intelligent. ChatGPT now has 1.2 billion users. It's really the fastest growing application ever. But what's interesting about it is that we've made way more progress with transformers than anybody ever predicted. In fact, people are now saying it's doing things that no one thought would be possible with transformers with AI. And one of the reasons why Jeffrey Hinton in the news, quit Google so that he can, warn the world about the dangers of AI. So a clever thing or an interesting thing is this emergent behavior. talk a little bit about that in a bit, but these are behaviors that nobody planned, nobody intended, nobody tried to make them do these things. They just did it all by themselves as they made these models larger. So it's surprisingly useful for many tasks. This is a rapidly changing field. There are papers coming out like every week, just about every day. Yeah. It's like it's moving so fast. And again, it's because it is so powerful and it is so useful. So you also have APIs that are available now. So now it's easy to make applications super intelligent just by plugging into this API. There's plugins now that are available so that you can extend chatgpt itself, and all of the other variations of transformers have come up with similar ideas. And finally, you can fine tune these things. And they fine tune really easily. And the fine tuning model can be made available, to you, because you create your own fine tuning model. And what fine tuning is just extra training on the model that's already there. And it works really, really well. So I'm going to talk about transformers. Before I do that, I'll just really introduce neural nets. You've probably heard about them, used them, whatever. There's all kinds of architectures, multi-layer perceptrons, RNNs, CNNs, GAN architectures, generative adversarial networks. There's many different architectures, and you have to kind of think about your architecture carefully and then build up these neural net structures. These things are great because you don't really have to know a whole lot about your area. You just throw your problem at this ball of goo and it just comes up with answers for you. But you have to know about the structure in order to get the results you want. Transformers, it's almost like a universal architecture. You just have to worry about how your inputs are formatted. You run them through the stack and you can get answers. So what are people using transformers for? Everything. The same transformer. You can use it for images. You can use it for sound. You can use it for language. You can use it for signal processing. It's a kind of like a universal thing. And one of the reasons that makes it universal is this thing called positional embedding, where what's embedded into every single input is positional information. And the neural net uses this positional embedding, plus, of course, the semantics of the input in order to do the processing. Surprising intelligent, I believe it's the DNA of superintelligence. Requires a lot of memory. It's trained on all of mankind's knowledge, but it's unclear how it reasons. We know it's reasoning because and I don't really like, so people have been calling it autoregressive statistical processing. I really don't like that characterization because it comes up with stuff that is not statistical in nature at all. It's really solving hard and interesting problems, but it's not clear exactly how it does it. Another problem, of course, is this, what's called the hallucination or imagination problem. It's great when you want it. It's not great when you don't want it. So sometimes in the middle of a problem, if it can't really find the solution, it'll just, tweak the definition of the problem and come up with a solution for you, which is not what you want. So that's kind of another problem with these things. But you can use prompt programming to make it smarter. And I will be spending a bit of time to talk about prompt programming. So one of the things we're doing with it at HealthGauge is we've done a whole bunch of investigation using just the transformer architecture itself to take readings off of this and do blood pressure estimates. And so far, it does just as well as our other CNN-based neural networks, but with way more flexibility actually. So quite intriguing. So let's talk about attention, which is this core, the guts of the algorithm. It really started with attention. The original paper, Neural Machine Translation, was written by Ben Gio and some of his students at University of Montreal. That came out in 2014, which led to this famous paper called Attention is All You Need. What the realization was, you could replace a whole bunch of neural network that people were doing with just this attention framework, because it could do all the same things. And so, and they also built out the transformer architecture, which then led to OpenAI implementing GPT and opening it up to the world. So in 2018, they came out with GPT-1. So OpenAI is a company funded by a bunch of billionaires and YC Combinator and Elon Musk, Sam Altman. And what they did was just throw a whole bunch of money at the problem, and they came up with GPT, which was amazing. And very quickly they did a few variants of GPT, GPT-1, 2, 3, 3.5, 4. They're supposedly working on GPT-5 right now. So GPT-4, well, actually, before I do that, I'll just talk about the realization with these models. So these models come in various sizes. And what they found was basically the bigger they made them, the smarter they got, right? Which is counterintuitive in a bit, because the number of parameters in these models is almost the same as the number of words that you input, which is not what you would expect with machine learning. Normally, you have a small, reasonable number of parameters, and you have boatloads and boatloads of data, much more data than your model. You throw that, and then that's your model ultimately learns. But these things just got smarter with size. And in fact, what happened is they started to generate what's called what people are calling emergent behavior. So that dotted line at the bottom, sorry, these are so small, but that dotted line at the bottom just represents randomness, really no ability to solve it. And the models got bigger, and still they couldn't solve it. And then they got bigger, and and then all of a sudden, at 175 billion parameters, they could all of a sudden do these things nobody expected. Nobody planned, nobody knew about them. They just did them. And so this is being called emergent behavior. And so there's a bunch of work that's coming out right now to try to explain this emergent behavior. A little bit about the numbers. So GPT-3, 175 billion parameters, it's trained on 500 billion words, not much more than the number of parameters in the entire model. So it's really quite this large model. Very expensive, took a long time to train. But a little bit about GPT-4. So supposedly 1 trillion parameters. That number hasn't been verified, but some people, in their paper, when they discussed their technical paper, they didn't say how big it was, but this is what people are saying. And it's trained on 1 trillion words. So, the same number of parameters as the number of words. So it uses self-learning. So it's almost like AlphaGo. Remember, AlphaGo trained itself by playing games. Well, this is what they're doing now with GPT-4. It incorporates something called instruction. So what they realized with these models is that if you train it with instructions for output at the top of your prompting, and we'll talk about prompting in a second, that it became that it did a much better job of solving a problem. So then they trained it to take instructions. So GPT-4 is trained on that. It's also trained on all of GitHub. So they took the source code, all the free source code in GitHub, they ran that all through the thing, and now it writes code. It writes amazing code. It's not always 100% correct code, but man, can it save you a lot of time and a lot of effort. It also uses something called reinforcement learning with human feedback. So basically they have people that look at the results and they decide which version of the output is the best output. And the reason that works is because when you make a call into the transformer, into chatgpt anyways, it gives you more than one answer. So then you can pick the one you like best. Reinforcement learning picks the one that's best. In GPT-4, it can handle images. So it does what we call multimodal reasoning. It can actually take the image, it can take the text, it jams it into one transformer, mashes it around, and it can do things. It can tell you what's in the image. In fact, it can take the image. So in the public announcement of GPT-4, one of the executives at OpenAI did an example where he drew on a piece of paper a screen. He drew it in pencil, and then he showed it to GPT-4, and GPT-4 wrote the code to implement that page. So that's pretty crazy, right? So it's multimodal reasoning. Now it supports plugins. So the most recent incarnation of GPT-4 allows third parties to actually put plugins into the system. And when GPT-4 reaches its limits, it says, oh, well, I know how to solve your problem, and it passes off the problem to an external system. And this is done for training, for for reservations, it's got a Wolfram Alpha plugin, it's got all kinds of crazy plugins. And this is like a new form of software now. And you think you got 1.2 billion users out there, a lot of motivation to try to build a plugin because you're going to reach 1.2 billion users. So it got really smart. So the blue lines here represent its performance on a bunch of exams. So these, sorry for the size again, but these are all like SAT math, GRE verbal, GRE writing, LSAT. And you can see, just ordered by how well it did, GPT 3.5, did pretty well on these human tests. GPT-4 passes almost all of them. These are ones that they didn't run it on, but on all of the ones, pretty much everything that you run it on, it performs better than humans, better than humans that are smart enough to even take the test, right? So that's the quality of its reasoning capabilities, right? So just before I get into the nuts and bolts of attention, I'm just going to talk about the application of transformers to image processing. So when people started thinking about transformers and image processing, they realized, well, what you could do is take an image, and an image is really just like a sentence, right? It's just divided up into patches, and you treat each little patch like a word embedding, right? So each patch is basically you spread it all out, spread the pixels all out into a vector, and you pass those off. You run it through the transformer. You have a little multi-layer perceptron at the top, and it does classification, and it's amazingly good, which ultimately led to DALL-E. So DALL-E 2, so all of the major systems that are out there, they use transformers in one way or another, but DALL-E 2 has a transformer jammed in the middle. So on the left-hand side, it actually does some attention-like processes to convert your symbols into, let's call it a pre-transformer sentence, right? It then runs that sentence through this transformer, and when you'll see when I talk about how transformers do, it kind of changes the semantics to ultimately match something called a pre-diffusion input. And so the final step is this diffusion engine. So that's the step way over here, this side here. So that's the diffusion engine. So it transforms a sentence into a pre-diffusion sentence, and then diffusion turns that into an image. And it works amazingly well. So if you haven't seen these images, so here's again some examples. These things are incredibly brilliant systems. So let's get into the transformer architecture. The transformer architecture has the original transformer architecture. So this is GPT-1, not 2, 3, and subsequent ones. But originally there were two, and this was what was talked about in the original paper. There's an encoder stack and a decoder stack. So I'll try to break these down into individual components and explain what they do. So the first part of the stack, and we'll just talk about the encoder stack, and then I'll explain a little bit how it all works out in GPT for once I get through that explanation. So you start with an input embedding. What the input embedding is basically words that have been converted into embeddings, but then you add positional encoding. I don't want to talk too much about that, other than to say that what it does is it has a mathematical equation that inserts information into every input that allows the transformer to know about the relative distance between the inputs. So the transformer can see the input embedding and it knows how far away each input is from any other input. And this is important because when it does the attention mechanism will treat things at different locations away from it in a different way, right? So you have input embedding. This goes into what's called a multi-head attention stack. This is where attention, I'll talk about multi-head in a second. And this whole processing here represents a block. It says NX. So in GPT 3.5, there's 96 of these blocks high, and there's about 96 of these heads, and there's about 12,000 dimensions for each particular word, right? So that's the kind of the size. It's massive, right? Massive. So let's talk about what the input is, so word embedding. So this is what a word embedding is. If you think about a word and you think, well, what are all the things that could be important about this word? What could it be about? How could it possibly be used? If you wrote all of the things that are important about on, and you gave everything a number, because they're in a unique spot, you end up with this word embedding. Now, these word embeddings are trained. So they're trained in the training process in order to behave in a particular way. But once they're trained, they have a very specific meaning. They position that word inside of concept space. That's the best way to describe it. Concept space is really interesting because it has mathematical properties. Concepts that are the same as each other tend to be in the same place in concept space, the same region. Concepts that are different from each other are farther away. But mathematically, these concepts, so if two concepts have a similar kind of semantic relationship, they have a mathematical relationship. So you can actually do this math and it works. You can say, take the king concept and subtract the man concept, add the woman concept, and you get the queen concept, right? So that's really interesting. And it's this mathematics of concept space that allows the attention mechanism to do what it does. So now I'm going to try to explain a little bit about attention and how it works. It uses this dot product idea to compare two concepts. So you have a whole word, got a big long word. Think of each word as being a concept. And what you're trying to do is figure out how the words relate to each other. Think about you searching for a movie, right? If you took your preferences and wrote all your preferences down, that would be an embedding, right? So all your preferences. And if you had the movies and they were all categorized in the same way, so they had an embedding that matched all of your preferences in terms of, concept similarity, you could quickly find the movie that most matches what you want just by doing this dot product. And it's a scalar, right? It'll just tell you this one's higher than that one. And you can and this is actually a thing now. It's called vector databases. So Pinecone is one, and you can use these vector databases that use this idea. So you can encode a bunch of stuff into this vector database, and then you can search for stuff in this vector database very, very quickly using this very concept. All right, but let's just say it's Monday. You have different preferences on Monday than you do on any other day of the week. They're related to your initial preferences, but they're different, right? They're contextually dependent. You might have different preferences that are different whether you're on Netflix or whether you're on Amazon Prime. So what you really want to do is convert to search for the movie. You want to query. And so let's call this variant of your input, let's call it the query vector. Same thing with movies. Movies, if the movie might have some sale on Mondays, right? So if you're looking for movies on a particular day, you want to take the original, let's call it the embedding for the movie, convert it into something that's a key, something that you're looking for. You want to take your preferences, convert it into a query, and then you want to match those up so you can then find the movies, right? So this is what attention does, okay? It figures out how things relate to each other. I'm just going to skip that slide. I'm just going to go here. So this is the math of the attention mechanism, the core. The input right here. So each one of these boxes is a vector, okay? These boxes are the query vectors. You take your input and you convert your input into 3 vectors: your query vector, your key vector, and a value vector, which is going to be what you're going to amplify with your dot product, okay? And you go through each one of your queries and you query it with the key, you get a scalar, you scale the value, so that gives you another vector, the value vector. You add up all the value vectors and that's your results. That's attention. That's how it works. So what that does is it takes your sentence and it transforms your sentence into a more abstract version of your original sentence. And so what you can think of, each layer in this stack, this transformer stack, converts inputs into increasingly abstract versions that the final version represents the token or the word that you want to add to the end of your input sentence. All right. So just a little bit more about that. So your inputs, so this is a block. All the blocks are the same. You take your block, you split it up into query key value. You then have this thing called multi-head attention. I'll explain that in a second. What you do is you use a residual connection. So the residual connections are really important because they allow information from the original sentence to continue to flow up throughout the network. So you have this residual connection, you add it in, you do normalizations. You then have another variant, another kind of transformation that's just a feed forward neural network. Just simple, it doesn't transform. Why is it important? It seems to be important. Half of the parameter space is actually sitting inside of these feed forward networks. And every block has its own set of parameters for the attention and for the feed forward network. And these are all trained with back propagation. So when you get to the final layer, you end up with a token, and the token is either right or wrong. And if, depending on how right or wrong it is, you get a loss, that loss back propagates through all of these weights. So typically what you'll do is you'll give it a block of text, lots of ways of doing this, but you could just take out one of the words of the block of text, train the attention on the missing word, and there's your loss. And so that's one way to do it. All right, I'll talk a little bit about multi-head attention here. Okay, so what each one of these matrices here, this is the input gets translated into the query key and value vector, and it gets split out into heads. Why heads? What the heads are is you take the input embedding and you divide the input embedding into pieces. So there's a bunch of pieces. So there's, some whatever in GPT-4, I think there's 25,000, parameters in the word embedding. So you divide it up into pieces and you solve each piece independently in a different head. So that's what the heads are. So each head is solved independently. And then so you take each head, you then combine all of these heads into one final vector. You just concatenate them all together. You run them through one other matrix. So these are learned parameters as well. And that gets your output, which then gets passed to the next layer. So there we go. We got through that. Does that seem incredibly incomprehensible? The first time I saw it, it was like completely mysterious, but if you stare at it long enough, you get it. So this is what it does at the very, very end. It takes the decoder stack output, converts that into a bunch of numbers, one number for each word in your vocabulary, using this linear layer, and then it runs softmax on that in order to get probabilities for words. And then you get your word. And then you do it again. So it's called autoregressive. It takes that word, it adds it input to the input. You now have a new sentence, and it does the whole thing again. And then you get another word, adds that to the input, do the whole thing again, and you get another word, and keeps going, and it builds up your output word by word, or as until it decides to stop. That's basically how it works. Okay, so that's interesting. ChatGPT trained to be a good conversationalist. What are the applications? Incredible applications. You can write resumes, cover letters. Like I've used it for proposals, memorandums of understanding, legal documents. I've used it for, I haven't done language translation, done a little bit because a friend of mine is entertaining a Ukrainian guest and I don't know Ukrainian. So we've been like doing some fun language translation. Here's something interesting about, well, actually, I'll leave that. So legal reviews, generating legal documents, medical diagnosis. So it passed the medical exam. So GPT passed the medical exam, passed the bar exam. It passed a Wharton business exam. So GPT is really smart. Sentiment analysis, you think about all the work that people have done to try to create sentiment analysis systems. This does it. It just does it out of the box, does sentiment analysis for you. Summarizing, you can give it anything and it'll summarize it and do a great job. It can check chemical reactions. It's really interesting. It knows all about chemistry, can plan trips. All right, so these are just some of the things that people are doing with it. I'm going to talk about one of the emergent properties is 0, 1, and few shot learning. So 0-shot learning is it can do things it wasn't trained to do. So this is 0-shot learning. Translation is one example. It was never trained to translate from English to French or any other language for that matter. It wasn't trained. So you think about how traditional machine translation works is you have these things side by side, you compare them all, you end up with a transcoder, train it transcoder, the transcoder matches all these things up, and now you get this translator. That's not how GPT does it. It just understands the sentence in English, and it understands the sentence in language. It converts the English sentence into concepts. It then converts those concepts into words in the other language. And it's remarkably good. And in fact, they've even shown that with a small number of input examples. I just saw this thing about Bengali, and they were, it didn't know Bengali. With a few examples, it understood all of Bengali, or most of it, and then could translate from into and out of Bengali, just like that. So there's this other thing that's emerging now with these things called prompt engineering. And prompt engineering, it's a new way to program. Think about that, because you don't have to write code now because ChatGPT is your program. It's all the programs. It's all in ChatGPT. You just have to figure out how to prompt it, and it'll be the thing that you want it to be, right? So now instead of writing, detailed code to, flip bits around and move vectors around, what you do is you move concepts around. You list off your concepts in a certain way, and ChatGPT is now your program, right? So it's so there's certain kinds of prompts that generate really interesting results. So for example, they discovered this prompt called chain of thought prompting, and the prompt is, let's take this step by step, one by one. And magically, if you add this phrase to your problem, it couldn't solve the problem before, but now it can. It goes up like twice as many problems now can be solved just by adding this phrase, because it turns out that if you force it to describe its reasoning process token by token, if it describes its reasoning process, it ends up with a chain of reasoning that it can use to come up with your answer, right? So that's interesting. So it also can do things. Another prompt that's cool is you could say in the style. So you could write code in the style, you could write poems, you could write books, speeches. You just have to say in the style of, and it'll just write it for you. Limericks, and then you can combine these things. So I'm going to spend a couple of minutes just on this concept of prompt engineering and how it works. So what you do is you write out this task description. So you think about, it's doing continuation reasoning. So it's reasoning about how to continue whatever you give it in the most logical manner, right? You give it a task description, you then give it some input that goes with your task, and then you put an output indicator, like a colon, and the answer is colon. So you have something that kind of keys the language model to know that it has to start generating text after your output prompt. So you have a task description. So this is an article followed by a summary written in an informal language. You can imagine that's your task description, and then your input is the article. So then you might put quotes around the article, or some bracket, say this is my article, bracket, article, bracket. And then you say in summary. So now what you do is it knows it has to do a summary because you told it that in the task description. But now you just say in summary, you put your colon, and that allows it to know that you want a summary, and then it starts generating the summary. So prompts could get a little bit more elaborate. So this is a conversation between a customer. So imagine you're trying to build a model for customer service people, and they're trying to help people, but what you want is you want to increase their capabilities by giving them access to ChatGPT's knowledge. So this is how you can do it in ChatGPT. So this is a conversation between a customer and a polite, helpful, customer service agent. And so then you have this little prompt that just says, here's the input indicator. So the input indicator is question of the customer, and then you actually have the question of the customer here, and then you start with your output indicator, and you can give it a bit more instructions about how you want the output to look, even how you want it to be formatted. So for example, you could say, please make your output in HTML, and then it would come back in nice HTML for you. Or you could say, put it into an Excel spreadsheet, or you could say, make it a JSON record. So then you could take that and plug that into some application. So anything you want, you just describe how you want your output. Prompting, so prompts can get more elaborate. You can put multiple examples. So I trained it to do SQL queries, convert to convert English statements into select queries, given a description of a model. And to do that, so this is old, like GPT-4, I didn't try it on GPT-4, but this is GPT-3. It couldn't do it, but when I gave it examples, it could do it, right? So then you have your example. Examples can be structured. So as long as the pattern, the textual pattern of each example is the same, it will pick up on that pattern and it will replicate the answer according to the pattern that you provide. Okay. So this is a movie review sentiment classifier. So we're trying to, and so the first example says the review, I love this movie. This review is positive. Review, what a waste of time. This review is negative. Review, I enjoyed this movie. This review is, and so there, this, now you're looking for its output. So just simply by creating this prompt, and you can reuse that same prompt with all of your input. You can reuse it over and over and over again. And that prompt is like a program. It's like a program for GPT, and it will then do that prompt thing on all of your input for you. All right, so some examples. Write a limerick about the effect of, AI on humanity. So easy. Write a short brief on the ethics of globalization, climate change. I require UI assistance. So you just tell it, hey, I want to write this thing. So I've done this with Streamlit and we actually use this. So now we have this thing in production. I just said, hey, I need this data. Generate a Streamlit page, a web page for me. Boom, put it into Streamlit and it runs. No programming. It's crazy. So regex, have you tried to work with complex reg expressions? Can anybody tell me what this reg expression means? It's like impossible. But if you put this reg expression into chatgpt, it'll convert this reg expression into words and it'll describe to you what that reg expression means, which is crazy. And I actually use that in coding where, like, I'm not a regex expert, but wow, it just gave me the regex expression. I stuck it in my code and boom, everything works. So create poems, music, education. You can get it to teach you like all kinds of things. You can do, it's get kind of a little bit funny. It's not really funny, but it's kind of, but here's the limitations. So its knowledge is limited to 2021 because that's when the training stopped. So supposedly the next version will have more updated training. Pretext and output is restricted to 8K tokens. GPT-4, supposedly it's 25K tokens, but I haven't experimented with that. But it can generate these solutions. It's a black box. Now, here's what's interesting, though, is if you give it an answer and ask it to explain why it came up with that answer, it'll come up with some explanation. But that's just, it doing its thing, how it actually did it in the first place. Well, there's a billion connections. So how do you know? But it has a limited chain of reasoning. So there's some things it just can't think very far about. And so I'll go into a couple of those in a second. So math, here's a math problem. Sorry about the text. I just wanted to show you. It generates like an entire reasoning process, step by step, for how it does it. But it's wrong. So solve this problem. If a ball is thrown in the air and lands 5 seconds later, how long will it take to land if it is thrown twice as high? Okay, so what do you have to do? You got to break the problem into parts, the apex, the throw part, so you've got these two equations, you solve it. But what you have to realize is that your initial velocity is different than the initial velocity when the thing starts falling. So what it did in its answer is it didn't realize this, and it made this mistake, the semantic error, and it comes up with the wrong answer. Originally, I had a simpler problem that I gave to GPT-3. If you drop a ball and it takes 5 seconds to fall, how long will it take if it's twice as high, right? So GPT-3 had not a hope. It just gave randomness as answers, and it would confidently, answer how. And in fact, GPT-3 even had problems with numbers. GPT-4 seems to have fixed a lot of these number problems. You ask it like, is 45 greater than 67? And it would say yes. But that seems to be all fixed in GPT-4. It's much, much, much better at math, but there's still just problems that seem easy, but yet it can't solve them. This is logic with space. So this is a spatial tiny little bit of spatial reasoning problem. It's not really that hard of a problem. You got a checkerboard. You take out the top two tiles offset by 1. So in the second column and the third column, you take out those 2 tiles. And now you want to know, can I tile this with dominoes? And it says yes, and it reasons out and it comes up with a tiling strategy. But if you look at the answer at the very bottom, it says the last domino can be placed horizontally to cover the first and fourth squares of the first row. In other words, you have to break the domino. So it just adds this constraint. It solves the problem by just arbitrarily doing something that you know that you can't do with dominoes, right? And then if you say, oh, well, you can't break a domino in half, it says, oh, I'm sorry, you can't do it. So then what you do is you point out, well, yes, you can, because you can just arrange the tiles a little bit differently. And then it says, oh, yes, you can. So sometimes it's just logical reasoning is flawed. So here's a predicate logic problem. This has to do with semantics. So the problem here is there's 4 people. They each have 2 different jobs, some constraints, who has what job. So that's what the logical problem is here, right? And it ends up coming up with a solution. Roberta has the chef and the police officer. But if you look at the very bottom, it says, this constraint here says, Roberta, the chef, and the police officer went to golfing together. Well, how could they go to golfing together if they're the same person? Well, maybe you can make this assumption, but so it makes this assumption that solves the problem. But if you tell it, no, don't make that assumption, then it makes it makes up something else, to solve the problem. Here's Wordle. This is interesting. And this is a really interesting example of prompt engineering. So you guys all know what Wordle is, right? You've got 5-letter words. You're trying to guess the word. You make a guess. If the letter is correct, it's G. If good, if it's bad, then it's B. And if it's kind of okay, but in the wrong spot, then it's a Y. Okay. It's hopeless. It can't seem to figure out. So as an AI model, blah, 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 my first guess is water. So the word is flask, it's guessing water. So it comes back, my first guess is water. So I say BYBBB. Okay, so there's your answer. So then it says, based on your feedback, it seems that the letter A is in the correct position and the letter W is, the letter W is present in the target, but in the wrong position. So it's wrong. Like it's just flat out wrong. And it can't seem to figure out how to convert this word description into something that it can reason with, right? So it's wrong, it's more wrong, it's totally wrong, it's wrong. But here's what you can do that's prompt magic. What you can do is explicitly tell it how to reason, and it will use your steps to reason. And then it works. It can solve Wordle problems. And so what you do is you tell it, here's your instructions. You have to positionally match each letter to interpret the result in the example. So I give it an example. Your examples can be structured however you want, right? So I give an example. B is bad, 1 in the first position. O is yes in the second position. A. So I give an example. For your next guess, you would exclude B and A because they are bad. You would keep S, 4, T5, the same place because they are good. So you give it these instructions about what to do. So you're programming it. So this is prompt programming. And when you program it, it works. It can now solve Wordle problems, right? So this is what we mean by prompt programming. So here's something that I wrote. So I wrote this application. The website, you can go and try it. It doesn't work, but it's a really, really interesting study. What I wanted to do was to see if I could prompt it to make chess moves and see if it could figure out how to make chess moves. So I wrote a program. When you move the chess pieces around, it generates this big, huge prompt, right? It fills in the prompt, and then it sends the prompt to ChatGPT, and it tells ChatGPT to bring back the results in JSON. I then take that JSON and use it to update the board so that you can then make and move. So I've got, so I've got some timers down here, by the way. By the way, these timers are code written by ChatGPT. I said, give me a clock. I want an analog clock, write it in JavaScript. And it just generated this code for me. Because I couldn't think of how to do all of the, the math to make that work. And I didn't want to. I'm too lazy. It just did it. So that's great. So anyway, but I wrote all the rest of the code. That was the only thing that it wrote. So anyways, so this is chess prompt programming. Pretend you are an expert chess player. Here's your Fen string, which is the description of the chess board. Here's the board list, black pieces, suggest a legal mood carefully. Now what I do is I start giving it steps to generate a move. So step 1, using only pieces from the board list. Now, my first attempt is to try to just give it the board and see if it could come up with the proper list. It was just hopeless. It just couldn't figure out how to do this. It's like it can't do the spatial reasoning thing, I think. So then I started giving it the entire board description as a big string, and it still didn't quite work. But it was a good experiment, and I learned a lot about prompting and how prompting works. So you can see I've got a bunch of steps. Like a chess expert, choose an ending square. The move is starting. So then what you do, and I'll just you can kind of see what these are all just the steps for what you would do to think through generating a position on the board. So then what I do is I tell it, use JSON format for your final output. But what I'm trying to do is in forcing it to fill in this structure, I'm trying to force it to take into account the input that I gave it. And so this method of forcing it to reason across its input is a good way to make it smarter. The other thing that you can do, so I tell it, tell me what board list you use, tell me what your black squares were, tell me what your legal moves are, tell me what band moves are, what's the move list that you're working from, what move do you recommend, what's the starting square, what's the ending square. Provide some comments, and it does really good comments. It's really quite funny because the comments look like they came out of a chess book or something. It's like, got to gain position in the center square, make sure your pieces are, don't, constrain the movement of the queen or whatever. And these are really, really good. The other thing I do is I ask for some trash talk, which is really funny. So then it comes back, you're gonna, I'm gonna get you now. And it's really great. It comes back, it's like a person, right? So, but then what I do is I say, make sure all of the output lines and the output examples. So sometimes it'll give you the JSON, but it might drop out some lines. So yeah, you don't need that one. Yeah, it does give you. So if you explicitly, so then you have to explicitly tell it, don't leave anything out. Here's the JSON structure, make this thing perfect. So then what you can do is something really interesting is you can ask it to explain its reasoning steps, given the steps that you gave it. And when it comes up with its answer, it'll tell you, why it did it, right? But in the end, it failed. It didn't work. It was a fun experiment because it doesn't have state space reasoning. It can't reason through everything. So how do we make it smart? So, all right. So methods for improving reasoning with transformers. One thing is we can do fine tuning. We can do prompting. We can do reinforcement learning. We can add plugins. We can do pre and post processing with a controller. So you put the controller over top of it. What people are doing is this cascading AI approach. So that's what Open AGI is doing from Rutgers. That's what Hugging Face is doing. They're building this way to cascade out to other AIs. But I think fundamentally the problem is that it can't do state space exploration. And so what I'm looking at is incorporating state space exploration into the transformer stack. And that is plugins. Okay, so here's my conclusion. Transformers are almost AGI. we needed to have a deeper understanding of how these things actually work. There's various, cascading and AI and transformer space exploration, I think, are the answers to get to AGI. Thank you. Sorry that took so long. Is there any questions?
Many. So can you hear me? Is there a big audience, Bruce?
Okay, so at the end of some reasoning process, or in the middle of some reasoning process, you realize that you don't have enough knowledge to solve the problem. Like, maybe chess, for example. You realize, oh, the person wants to make chess moves. I don't know how to make chess moves. So what you do is you take that part of the problem and you send it over to another engine. Could be locally, or it could be on the internet, it could be somewhere. And then that engine solves the problem for you, brings you back the results. So you can have these domain specific AIs, right, all over the planet, and they can solve problems. Now think about that. That thing could do the same thing. It could take your problem. Okay, well, I know how to do opening moves, but I don't know how to do end game. It looks like you're at the end game, and it'll pass it off to something, right? So then this problem can cascade, and now you bring your answer back. So that's cascading AI. Okay, what's their quick? Can you read it for him?
Randy is trying to.
Oh, Randy's trying to say something. Okay, go ahead. Oh, hang on. Let me put you. Just let me do something here. Oh, hang on.
Oh yeah, you can
Just
escape
wait.
the
Just
screen.
wait. We will get to you, but we have to change our volume. Oh, hang on. I know what to do. There we go. Okay, go ahead.
Thanks, Bruce. So the first thing to say is that we have to have some offline conversations because there are many things that I've learned about the application of transformers. I wanted to say first, I appreciate some of the details of your interpretation of the mechanism. So I will talk to you offline about using some of those when I explain transformers. I like the enthusiasm, but I want to provide some caution for your enthusiasm. Let me start with what you said about the enthusiasm about medical and bar law exams. So you may know that we've been using transformers in the legal reasoning competition since 2014, I think. 2014, the U of A team essentially passed by achieving more than 70% of the Japanese bar law exam. But that was almost a decade ago. And what it really taught us in our subsequent COLI things, it taught us that the exams were designed by people who were testing memorization and rote knowledge, which is exactly the case for the exams you mentioned in the medical exam and the bar exams in the US. So the good news is that such a device can do this means we have to reevaluate what humans are good at. And we've seen that reevaluation go through several iterations. Another thing to thank you for is that you didn't use the word generative, because transformers as encoders of knowledge can be used, as you've demonstrated, in many ways. So thanks for that. Two more comments, and then I'll give you. Then I'll pause. We've heard claims, and you and I have discussed this, claims about so-called automatic programming for years. So for example, inductive logic programming says you don't have to program anymore, just state a few facts about relationships of data objects, and you can search through the space of all possible logic programs, find the one that you like, just like what you said about prompt engineering. So there's caution there that I think. So there are many other things to say, but the reality comes down to explanation, and there is no measure of the ratio of wrong outputs, factually incorrect, to take a small subset, versus factually correct. And that can't be done for a number of reasons. First, these are moving targets, despite what people say about 2021 having no text embedded since then. they're still changing all the time using resources that academics like us don't have. So maybe a little bit more about explanation, which is essential.
Yeah.
Anyway, offline we can continue because there's a lot to talk about.
Well, I would be more than honored to spend time with you, Randy, to get your insights into this. This is, you've
Yeah, we can work on it together. I'll show you some of the recent papers we've worked on that demonstrate the logical incapabilities. So I just finished 3 this week actually, so we can share those off.
Yeah, so that's great. I mean, I kind of want to explore that idea that I have with you, where the nut of my idea is that in order to explore a state space, you need the ability to restart, right? So iterative deepening is the basic mechanism. Iterative deepening and beam search. Those are the two core mechanisms of all reasoning, right? So whether it's min max
And you brought up an important point about application specific things. So I like the application in your signal processing because you can potentially engineer a transformer to give you value that's judged by the subject matter expert that doesn't need the explanation because you know what you're looking for in the signals, for example. So that's probably a high value application. On the other hand, in legal reasoning, I can demonstrate for hours why the current transformer technologies are not sufficiently strong to be used by themselves. Anyway, that's enough.
Definitely not used by themselves. But if you're trying to generate a boilerplate, oh my gosh, it's amazing. And I've used.
Well, in fact, we don't even use them generatively. We use them, for example, for paraphrase, because much of the legal reasoning requires you to understand the challenge of paraphrasing language.
Yeah, that's a very good application. You just give it a whole bunch of legalese and you say, here, explain this. And it'll convert it into natural language for you, like really, really well. So, but again, you as you pointed out, I agree, you wouldn't want to just not have your lawyer, right, look it over because it makes mistakes, right? Definitely. And
well, the reality of law is we do have a standard of correctness which cannot currently be conveyed by prompt engineering, I guess is one way to think about it.
Right.
Anyway, I've taken up enough time, so thank you. And I will arrange a meeting with us maybe at some regular basis following up.
Perfect. I'd love that. All right. Any other questions? Go ahead.
So I have 2 questions. First is on understanding. How big of a problem do you think it is? The second one is about your claim about us being close to Asia. You spoke about some limitations of the private headcounts. That seems pretty problematic. Why do you think those are important?
Well, I didn't say that they weren't important. So I'll take your first question, which is about hallucinations and how much of a problem it is. It depends on what you're trying to do. I mean, if you are asking it to tell you a bedtime story, then you want it to have a rich imagination. But if you're asking it to solve a problem, a very specific problem that requires specific reasoning, well, then maybe it's not so good. But you're going to look at this output anyways, right? So and in some situations, it doesn't hallucinate. It doesn't hallucinate when it has clear knowledge of how to solve the problem. So if you're trying to get it to write code, it's not hallucinating. It just writes the code because it knows. But if you ask it, who's going to win the election? Well, it might make up some facts because it might think that it needs it in order to, to reason about the current state, right? So you definitely, if you're asking it for facts, you definitely want to fact check, right? And so people have written these things, auto GPT and other things that, they have they do fact checking. So and it's not that hard to do because you could ask diffbot, right? Or something. You could ask some kind of semantic engine that has the facts. And so it depends on the context in which you're using GPT. But if you're trying to tell a person, if you're a therapist and you're trying to advise a person, well, you definitely don't want it to hallucinate. And there were some, problems in early days where the thing said, well, you should kill yourself. I was like, and so that was its advice, right? So, so sometimes it can do that. But what people are doing is they're layering in these guardrails on top of it. So additional engines that are designed to fact check, additional engines that are designed to find hallucinations, additional reasoning. And so this is why I think we're on the verge of AI, because if we can implement these guardrails and if we can solve the state space reasoning problem, I believe that we'll be there. It will be AGI. It already seems like AGI. Like if you use it to try to write a proposal for you, like I was doing this proposal for this, AI center for this other organization. And I just asked it, I said, hey, give me a proposal. Here's what I did. I said, what are the major sections of this proposal? And it said, oh, section 1 is this, section 2. And it told me what all the sections were. And then I said, well, do section 1, do section 2, do section 3. And it just wrote the whole thing out. There's like, who can do that? And it was instantaneous. It is on the verge of AGI already. Its output is indistinguishable from super intelligence people in many, 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 many areas. There are limits. Those limits, I believe those limits will be, surpassed in the next year, 2 years. Go ahead. Sorry, you're next.
Sorry. You want to ask a question?
Oh, yeah, go ahead.
So I think some of these complex things it's able to do well. And some of the chess playing games, it knows how to play chess.
Yeah.
But simpler things, the algorithms cannot do. So I don't know where the current version of GPT is, but I think a prompt like give me a sentence without the letter E, it fails at that.
Yeah. Mm-hmm. Yeah.
I think that kind of simple things and the common sense stuff.
Well, that's partly how it's programmed, because it's programmed using tokens, not letters, right? And it knows, but if you ask it to break out a thing into letters, it can do that. But if you prompt it properly, so some of the to some degree, it's like a person. If you tell a person here, go to the store and get me some chicken, and it comes back with some raw chicken, you go, well, I didn't ask for raw chicken, I want to cook chicken. Well, if you're not very good with your prompting, you get not very good answers, right? And it's the same thing with GPT. If you give it really good prompting, it gives you good answers. So even with your prompt question, there's actually a way to prompt it to actually get that answer that you're talking about, right? And in fact, now you can have transformers that are designed to write prompts for other transformers. So you can ask the transformer, how do I prompt you in order to be able to answer a question like such and such, and it'll write out a prompt for you, which you can then use, and now can solve it.
It's actually a prompt optimizer.
Yeah.
There's a prompt that makes the prompt better.
Yeah, that's I believe that, so that's how people are using these things, right? You had your question.
So it's almost a follow-up that question. So you experiment with a lot of with GPT.
Mhm.
Or ChatGPT. Then ChatGPT came out and you discovered that some of the problems that GPT-3 was failing on ChatGPT better.
Much better.
GPT-4.
Yeah.
But the experiments that you talked about say, this problem fails, but if I talk to properly, then it does better.
Yeah.
Yet you were talking about reasoning within the same model. So if it failed and then it succeeded because you gave it the proper prompt,
Mm-hmm.
and the proper prompt has all the steps to follow.
Mm-hmm.
And the reasoning is not in the language model, the reasoning you gave it. you did the reasoning for it.
Yeah.
So can you still talk about the reasoning that happened when you were in the car?
Well, yeah, yeah, so good point. I mean, but you know, it has to be smart enough to follow that reasoning. So there's a lot of intelligence, like just because somebody gives you a list of instructions, you know, if it says here, this is how you make a nuclear bomb, write all the instructions. I couldn't make a nuclear bomb, you know, even if I had the instructions, right? So you have to, you know, so it has to have enough knowledge to interpret those instructions and, you know, and follow through those steps, right? And so you actually have to give it credit for that. But, you know, you can also imagine that with future versions of that transformer, you could get rid of that prompting technique. And in fact, this is what GPT-4 does. GPT-4 has kind of like built-in prompting mechanisms that GPT-3 doesn't have. And that just make it smarter, right? And in fact, learning the prompt is a form of learning, right? In fact, you could even, and so this is, you know, yeah,
There's some the conscious reasoning, the right conscious.
yeah,
It's common sense.
yeah, yeah.
So if you ask somebody doing business,
Mhm.
you don't have a kitchen.
Yeah,
You want it.
yeah,
So it should be.
yeah,
I don't even think about it being at all.
yeah, yeah.
So
Oh, yeah,
I don't think about it.
Yeah.
That I do conscious.
Yeah.
I would do unconscious. There's, I don't even think about it.
Yeah.
after the fact.
yeah. Well, there is a lot of common sense that it has just from reading all the text of mankind. So it has a lot of common sense, but there are gaps. I mean, there's gaps that we only have those, you know, we filled in all the gaps because we live, right? We, you know, we experience all this stuff with our physical bodies. So, and it doesn't have a physical body. There's a tons of knowledge that, you know, that are just common sense facts that you could only get by living, you know. And so this is, you know, really some research and people are actually looking at this, you know, give it, you know, give it a life from a baby, right, all the way up to a person, give it every single last, you know, question, problem, and then now it has all the facts. So the more kinds of the more data that we have to illustrate the problems that we wanted to think about, the smarter it's going to be, right? But there's lots of problems that are, there's lots of gaps in knowledge in, you know, all of the words of mankind.
So when we wanted to build fast things, we didn't copy the cheaper. So the car doesn't copy the cheap. It has wheels.
Yeah, yeah.
When we wanted to fly fast, we didn't copy the birds.
Mm-hmm.
Now we run faster than the cheetah and we fly faster than any bird.
Sure.
Yes, for the computers, when we were thinking of building intelligence computer,
Mm-hmm.
we were arrogant to think that anything that would be smart like us has to be like our brain.
Mm-hmm.
For a long time, they were saying, well, it's far away from the brain. Yeah, it has these neurons, but it's not like our brain.
Yeah.
So it's not our brain. We didn't reach our kind of intelligence. What recently Jeff Hinton left Google, so last week.
Mm-hmm.
One thing said in one of the interviews said that he changed his mind about the danger of AI when he realized that actually, even though it's completely different than how we function, it can become better than us.
Mm-hmm.
It can become, it's not yet, but it can become. We don't have to copy basically our brain
Mm-hmm.
to make it better than.
Yeah, yeah.
So what do you think about that?
Well, you know, what is thinking? Thinking is manipulating concepts. That's what thinking is. So concepts are these, you know, these abstract notions of how does this relate to that? That's what a concept is. And machines can manipulate concepts using various kinds of neural nets or transformers. Transformers aren't really neural nets. Transformers are these, these dot product things with weights at the end. There's no activation function.
The best representation.
Yeah, it's a great. Yeah, so it's a great representation.
It's the best.
But there might be, well, so it's digital, right? Because you take the concept and you divide the concept up into a bunch of numbers, and then you train the embedding system. So the embedding system converts that word into the, the correct numbers, right? And the training is done on all of the words all the sentences that you put into the system. So the embedding, so the embedding mechanism that converts tokens into concepts is again trained. But you could imagine bigger numbers, maybe if you had much more bits per word, it would be smarter. You could also imagine a continuous concept space rather than a digital concept space. So maybe you could invent a new kind of processor that processes, that holds in memory, an embedding, and it does it without digital form, right? So you can imagine, something like that, right? So I can imagine other kinds of intelligence mechanisms evolving, but they all fundamentally do the same thing. And digital concept manipulation is good enough. It's obviously good enough for GPT and does a pretty good job, it basically shoves these concepts around in concept space, and eventually, here is that concept. That concept is the entire sentence. Here it is. So the word that is attached, the closest word attached to that concept is this word. So that's what you use as your continuation. And it's good enough, right? As long as it's reasonably continuous. And in fact, this was a great paper that came out that described the problem of, these large, why, what they proved was you can only achieve certain levels of thinking when you have models that are large enough. And what they showed was that if you don't have a large enough model, you have discontinuities in the concept space. So two concepts just cannot go together. So if because you need to interpolate along a curve as you push a concept along. And if it stops because there's this, digital gap between where it is and where it needs to get to, then that concept will never make it along that curve.
When you find a representation for that word, it would be fooled by its concept neighbors on one side, and fooled by the other concept neighbors on the other side. So I take the example of the word lawyer in French. Lawyer is avocat. And avocat is the avocado. So the same word.
Yeah.
The same way. It's like the same type of fruit as well as a profession.
Yeah. Well, so the
does it really be in the space of fruit, or would it be in the space of profession? Can be fooled by both.
well, okay. So what the embedding does is it encodes all those possibilities. Like all possibilities are now included. When it
Close to both.
okay, yeah, and it is close to both, right? So if you looked in concept space at advocate, right, and looked at lawyer, you'd find them in related, and other words that are similar to lawyer will be similar to advocate, and they'll manipulate it in certain, or counselor, right? So, but the query mechanism, the attention mechanism, knows that there's a difference, and that difference is implicit in where you are in the reasoning process, and positionally where you are in the word. So at the start of at the very, very start, at the very base, the word the has a specific meaning, and that is what the query key value is for. It basically figures out in that position, at that level of reasoning, I need to transform the word the into this concept. And that's what the query does. And then there's, the lawyer. So the lawyer has a specific meaning in that context. That's very, very different than if it was the lawyer way at the end of the sentence or wherever it is. And so there's a key, right, for the lawyer. And it converts the lawyer concept from the embedding into the key that will be used at that layer in the transformer stack. As you go up the transformer stack, the queries and the keys are different. And the values, query key value. And they're different because you're trying to think about those concepts in different ways as you get closer and closer to your final word that you're going to output.
How big should the stack be?
The bigger it is, the smarter it is. There, as big as you can make it. You know, you just have to give it lots and lots of output and train it and do self-supervised training.
Well, isn't that an intelligent solution?
What's that? Sorry?
So you're saying that we could just make the network bigger. Isn't that kind of intelligence? Like, I could imagine that if my head was the size of this room, I could think about the document and stuff.
Yeah. Well,
It wouldn't be very-
well, I agree. And that's why I think that we can make them smarter. And one way that we make them smarter is through this, you know, this mechanism that I talked about, which is state exploration. So state exploration. So let's just say that you're trying to solve the 15 puzzle, right? So you know what the 15 puzzle is. You got a tile of puzzles, 4x4. You're trying to move the blank around in order to get the pieces to get into the right position, right? It's if you just moved randomly, you would never solve the problem. Never in a million years. Like maybe a million years, maybe a billion years, right? But if you know how, like the relative difference between the state here and the state here, and you can compare them, then you can explore the state space. And that's what heuristic search does. Heuristic search says, here I have a heuristic, just count the number of pieces that are in place. Well, there's a heuristic. And now you know that that concept is closer to the concept that you want to be at than this other concept. And so again, so then what you do is you just restart, right? So iterative deepening, you go to one level and then you figure out what the best moves are. Then you back up to the start. Then you go 2 levels and then you back up, go to the start, go to 3 levels. And each time you iterate, you know which paths are worth exploring, right? And so then you only explore the paths that are the best paths. And then and it works really well. So all automated reasoning is based on this idea. Well, actually two concepts, iterative reasoning and kind of beaming the paths that you explore. And with that mechanism, I believe that we can significantly reduce the number of layers required to do intelligent things.
So, we think that this is how we're going to allow us to make transformers or other smaller than that.
Yeah, so there's already Hyena. I don't know if you've seen Hyena. So Hyena uses a transformer-like system, but it's an attention-like system, but it's not attention. They call it subquadratic, comparisons, and it can handle sequences much longer. So they're doing sentences they're doing like million token sentences, like GP. What's that?
That's not a sentence.
Well, yeah, like a whole book, a whole database. So imagine every single query is like a map, like the whole database. And these things are, so Hyena, like you can go and look at this research, and it's really quite incredible. Now, they've shown that it's equivalent to attention at sub-billion parameter models, but they haven't done anything yet with post-billion. So it's not clear that you would get these emergent properties yet. So there's still a lot of work being done on it. But it's a great idea. So altering the attention mechanism in slight ways, which is kind of what I'm proposing, I think will make it smarter. Yeah, sure.
Some people would say that it's easy to train on all the people in the world. You don't have to use generalized communications, whatever you do. What do you think about that?
Well, okay, what does generalization mean? Generalization means homomorphisms. It means climbing this concept stack, right? And so then you can generalize if you have a method to reason about the semantic similarities in the general space, right? And so so I think that that's what it does, frankly. That's what I think that you end up moving these concepts over into this homomorphic space. And now when you reason in this homomorphic space, you're able to solve problems that you couldn't in this other space because, you know, the concepts don't, you know, meet very well, right? So, so that's what I think, you know, that's what I think it's actually doing. And I think it works really well. You could ask it to generalize. In fact, you can ask it, you can say, compare a cat to a person, you know, and you can ask it for these kinds of comparisons. Or you could say, compare a cat to a summer day, you know, and it'll come up with all, you know, with these semantic comparisons that, you know, that easily generalize concepts across these concept spaces. And how does it do it? It's not even trained to do it, but it can do it, right? So I think again, this is an interesting area of research. Why is it able to do that?
Thank you.
All right. Okay. Thank you, everybody.
Don't forget to stop for the vote.
Yes, stop. End.